Welcome everyone to a special edition of Moonscapes. This is number 23 in the series. And as you can see by what's on the screen in front of you, this is a special edition. We do not have an image of the moon. As I mentioned last month, the months of December, January, February, could even be into March here in Connecticut, can be brutally cold. And last January, I had the use of a nice little shed off my son's garage, which we could run wires out to a telescope mount that was left set up for the entire winter. I kept it covered, and when I wanted to do an observing session on one of these cold nights, I would just go out and uncover the mount, drop the telescope tube assembly on there, and the mount was already aligned, and we turned on a few switches and powered up the scope, and off we went. I did sessions when it was down around 0. Well, it is January the 2nd, 2014. Happy New Year, everyone. And right now here in Terryville, Connecticut, we have temperatures that are about 9.5 the last time I looked, and we have raging snow going on. We're going to have near blizzard conditions here in central Connecticut. They've predicted blizzard conditions out in Long Island, but we'll have near blizzard conditions here overnight. They're predicting 5 to 10 inches of snow, possibly even more than that, and brutal cold temperatures. So I'm not going to be observing the moon anytime in the near future. So I promised you something new, and so I came up with this idea tonight. I'm going to take you back a little bit, and I'll show you a little bit about what I used to do in astronomy, some of the things I did do before I retired, and lost the use of the nice observatory I had. The image you see here on the screen in front of you is an image that I took of the comet Hale-Bopp. I believe it was in 1996. This is an old film version image. It was taken with a Minolta camera, 35mm camera, with a Fuji, I think it was Fuji 1600 or Fuji 1200, I forget which, one of those higher speed films. And it's about a 10-minute exposure with the camera attached to the telescope, so the telescope would track the sky and give us the stars so they wouldn't be trailed, and of course the image of the comet. Now notice this image of the comet. You know what, I wish I had a pointer, and for some reason I didn't get myself one. But if you notice, my finger is going to be in the way, yeah. But notice up in here, that blue streak. That's the plasma tail that this comet and many of the major comets that get really bright have that plasma tail. And then the other tail back in here, and I'm going to have to find something to point with because this is not working out very well. That's the dust trail, and that points and curves away at a different angle. So this was just something that I slapped the camera on the telescope and took a photograph of it. I actually had taken this outside my observatory. It was taken up at an area called the White Memorial in Litchfield here, and I'll slip this photo in next. And there is an image, the same comet, taken several nights later. And this is taken up in an area called the White Memorial Conservation Center in Litchfield, Connecticut. And the Manitowoc Astronomical Society, which I'm a member and a founding member, I helped form this group back in the mid-1980s when Halley's Comet was around, built this slide-off roof observatory. And that is the building you see behind here in the background with the comet just over top of it. That is the roof of the observatory, It looks kind of just like a backyard shed, but the wheels are mounted, or I should say the roof is mounted on these heavy-duty casters. And when the roof is unlocked, it can be hand-pushed off to the side and exposing the telescope to the full night sky. A pretty neat setup for our observing sessions for our club at the White Memorial in Litchfield. That telescope that you see in the foreground is, I no longer have that instrument. I sold it. Kind of had to pare things down when we started to retire and move out of the house. That is one of the classic old Cadillacs of the 1950s and 60s. That is a Unitron 4-inch telescope. That is a classic model that us amateur astronomers used to drool over. They used to come on these full-page ads in Sky and Telescope, and we used to look at them and just really drool and wish we had one. And I finally bought one later on. It's a great instrument, long focal length, f/15, so it's good for the planets and and the moon and things like that, but not good for deep sky objects. If this is going to work for me real quick, I want to show you something just real quick, and then I'll go back to some of the CCD imaging work that I did. This is a little tough setup that I've got going here, so I don't know how well this is going to work. So if I kind of bounce the image around for a few seconds, just give me a chance to get it settled down. This picture I'm going to put up next is actually the first major telescope I bought. I bought it after I come out of the Navy. I'm just going to put this in here, and I'm going to have to readjust the camera once it's in. This is a Criterium RV6. And I'm going to have to back off the camera a little bit so we get a little better field. Let's see how much of this we can get in. This was also advertised in Sky and Telescope magazine. This is a 6-inch f8 f8 6-inch reflecting telescope. It's the first telescope that I really consider as a major instrument for me to use in astrophotography and for normal viewing. I'm trying to make myself a pointer out here out of a piece of paper since I forgot to grab a pencil. But this had a clock drive on it, and you could put it on an object and it would track it nicely. And you could even do some astrophotography with it. It had its limits. Astrophotography, you have to carefully guide the telescope as it's running. You have to keep a second scope that's mounted usually in the back of this with a crosshair eyepiece on a star, and track that star using slow motion controls during the whole exposure, so the image doesn't drift. And to do that, you right here is this section right here is called the polar axis, the right ascension axis. That's set up so that axis is actually set up so it's parallel with the polar axis of the Earth. So when the motor, which is back here, that box in the back, it runs the telescope in the opposite direction at 1 revolution per day, and that's how we get our images out of the night sky. And this telescope I used for a good many years, and I used it for a lot of work when I was doing variable star studies, when I was a member of the American Association of Variable Star Observers, and I was making variable star estimates, and I hope to get to a demonstration of that here in a second. Now, one of the main things that came up early on was that you're working on the outside, just like we're complaining about now, the cold weather, and it's too cold for me to be out there, and you want to build an observatory. Well, this, and its print's kind of curled up and it's not showing up real well. This was my first observatory. It's what's called a slide-off roof observatory. You can see there in the background all it is a square outdoor garden type shed. As you can see there, it's 8 foot square, and the roof is built on metal rollers, and you build the extension track out here so you can slide the roof off the building and onto those supports, and you observe. You're in the observatory somewhat comfortably. The problem with this setup was you're just as cold inside there as the air temperature is outside. In other words, if it's 10 degrees outside, it's 10 degrees in there, because this was a day when we were using photographic film. And we didn't have the CCD detectors where we could set up in a separate room and warm it, and can automatically controlled and computer controlled telescopes. This was a day when you had to be out in the cold and actually doing the work. But this was my first observatory. It was built with the help of a friend, and it got used. This was built in 1969. And I used this building as is until about the early 1980s when I put a dome on it. I started with an 8-foot dome and eventually enlarged the whole building out to 12 feet square and put an 11-foot dome on there. So let's move on here a little bit. Not sure. Oh yeah, here, I can do this next. This is a print that was taken several years before I moved. This is kind of the finished version of what my observatory ended up looking like. This, believe it or not, is the same basic structure that was in that roll-off roof observatory. I just expanded the walls out. As you can see, I'm getting a little round circle there because I'm using the camera to actually use the image of the moon, and it's having a rough time handling these photographs. But you can see the building is basically the same square building, only it's out to 12 feet square. And that dome, and in this view it's silver. I kept going back and forth. I couldn't decide whether I liked the silver or the white better. In this view, it's in its silver state. Now, that dome weighs about 500 pounds. I burned out 2 jigsaws cutting plywood arcs out to form the dome. The dome was covered with sheets of cardboard and then fiberglass. Now, I'm not good at fiberglassing, and if I ever were doing it again, I'd have somebody come in and do the fiberglassing for me. The fiberglassing came out so rough that I actually went and ordered a special roll of aluminum flashing, very thin flashing, and attached it over the framework from the fiberglass. I just didn't like the way the fiberglass finish looked, and I ended up with this. That's not quite the finished look of the observatory, though. Because part of it is blocked. And we're going to go back and remove this photo. Back to that original. And this is actually the way the observatory ended up looking here. And let's zoom in on this now a little bit better. It shows up a little bit better. This is the way the observatory ended up for my serious work, my CCD work and my research work in variable star astronomy. As you can see, the building, I've covered it with texture 111 and made a little better finish. The dome is now white. And I hit the mic again. That's probably going to sound terrible. But notice off here in the back, see that little extension out here, that was added on in 1996. It's got that little window in it right there. That is a heated control room. It's 5 feet by 8 feet, and it's about the size of a large walk-in closet, or small walk-in closet, however you want to look at it. And I could sit in there in total comfort, 68, 70 degrees, and take my images from wherever I was doing, variable star research, or taking just pretty nice pictures of the sky, which I'll show you a few. Now, actually the way it worked was you would go in, open up, flip a couple switches, unlock the dome and open the dome, and then you would go and do your setup. And this is the telescope that finally ended up in there. And this is my Meade Schmidt Newtonian 10-inch. It's kind of a little overblown. I wonder if I can bring that helped a little bit. That's a 10-inch f4. The mount in here, that's an Orion Atlas EQG mount. Now this instrument I'm still using. In fact, there are a couple of runs done on the moon. A couple of my Moonscape videos were actually done with this instrument. But here you can see the advantages. It's set up in the observatory, and it's permanently set up. This polar axis right here, that axis that runs right through here, is pointed to true north. And by being permanently located in the observatory, you never have to worry about changing it. It's a little bit of a pain in the neck to align and set up to a run every single night. It's much easier if you can go out there and it's already lined up like it is here, and you just open up the dome and turn on the drives, and you do a little setup procedure where you just locate two stars, and you tell the telescope that this star is Aldebaran, this star is Rigel, or whatever star it is. You tell it what time of day it is, and you've already loaded in the longitude and latitude where you are on the Earth, and the telescope knows where it is, and you just push in the object you want to see in the little hand control, and off the telescope goes and finds and takes its pictures. Now, I used to do a lot of plane photography, astrophotography with film, and I later switched over to CCD imaging. And I'm going to put this image up for a reason. This was a little bit of work that I did on the planet Mars. I'll have to pull that back a little bit so we can get the whole image in. And this shows something pretty neat. The CCD camera that I used is a black and white camera. But notice the finished image, which is up here on top, right here, of Mars, is in color. Now, how do you do that with a black and white camera? Well, down here, I'm not too sure if that focus is really sharp or not. Let's try auto. Oh, it doesn't like auto. There it goes, but it's not really good. Let's take it out of auto, bring it back. And that's way out. Okay, you can kind of read it. Down here it says red, green, blue. And what we've done there is we've taken an image in black and white with a red filter to get the first image in red. The second image is a black and white image taken with a green filter. The third image is an image taken in black and white with a blue filter. Now notice the difference in the amount of detail you see in each one of those images. The red and green aren't too far apart. Now this does not display the image really well. But if you notice the blue image, Notice the white down on the bottom of the image here that does not show up nearly as well as it does in the red and green. So that's showing you what it's doing. It's separating out the colors and what's strong in one color and not as strong as another. Notice in the finished image up above of Mars, notice that polar cap and haze, how nice and well that stands out. Well, look, in the red and blue, in the red it's not even there. The green, there's a hint of it, but it's blue. Most of that white in here is coming from the blue part of that image. Also, it's hard to see in this image because of the reproduction of copying this photograph to the webcam. Notice off on the right-hand side of the disc over in here, I know you really can't see it here, but believe me, there is I can see it, it's there. There's a very slight white haze. That is also coming from the blue image over on this side of that blue image. And that is morning mist and clouds that occur on Mars at times. And that is coming from the blue image. But anyway, that's how you get color images from a black and white camera. You take 3 images, a red, a green, and a blue filtered image. And for deep sky images, which we're about to go into, you can add what is called a luminous, which is just a black and white image, and go longer exposure, building up more data. And when you add it all together, you get the color from the RGB, the red, green, blue, and the deep, what we call luminous, allows you to get more detail, deeper out of the image by combining the 3 colors into one and taking a long exposure. I'm going to move along now and show you just some of the imaging I've done, and if I have time, I'll try to show you just a little bit of the research I got into. I may have to save that for another video. This is taking a little bit longer than I thought. This next image I've got coming up, that is a gorgeous image of the comet Holmes. This comet, I can't remember just how many years ago it was. It wasn't that many years ago. I would say maybe around 2005, 2006. I'm not 100% certain. Trying to adjust the colors here. It's giving me a little trouble here. I don't like the way this looks. It's not. It's really overdone. I think I'm having a little bit of trouble with the lighting I'm using to light these images. It doesn't. Some of these images don't like that. Don't like the color. It's really overdone here. That blue is really over enhanced here. But anyway, that is Comet Holmes. That is roughly only about a 7-minute exposure. Now, when you take pictures of comets, sometimes you run into problems. The comet moves at a different speed than the stars do in the background. So if you take your telescope and you guide it on the stars, and you just, let it go, the comet will come out smeared because the comet is moving with respect to the background stars. Now, I was lucky enough where this comet's speed was slow enough where I could guide on the stars, and the comet stayed nice and still for me and presented a sharp image. This image of this comet actually appeared on our local CBS news affiliate station on the news section they did on the comet back when it was out. I got contacted by that news station, and they somehow got my name as doing some astronomical work, and anyway, this image ended up on TV. Notice inside this comet, right there, that looks like that little fan there. That is actually a jet coming off the core of the comet. That's actually the very core of the comet, and that's some of the debris that's coming off of it. This comet shot up in extreme brilliance. It was very, very faint, obscure, not even really worth looking for. in over a 24-hour period, it increased by thousands. I forgot the exact number of times. I've heard thousands. It's just an incredible amount of brightness, from something like 16th magnitude down to where it was faintly visible to the naked eye, and in a telescope, it was a beautiful object. This was taken with a slightly smaller telescope than that main telescope in the observatory. It was taken with a smaller image that I used to guide my images, but it also works as a wide field imager. So I'm going to move on to now to some of the deep sky stuff that I did, and we'll see how these look on here. I'm not sure just how they're going to look. This next object, that's one of the better color-looking schemes I've gotten so far. This is the object M27, Messier 27. Charles Messier, the discoverer of comets, found a bunch of these things that bothered him, and so he cataloged them, and so when he came across them next time, he would know what they were, and he wouldn't bother with them. Believe it or not, this is a death site. This is what's going to happen to our own sun in about 4 to 5 billion years. Right in the center, let's see if I can point to it with a makeshift pointer right through together, but that star right there in the center, it's reached the end of its life cycle. Stars live out their lives by turning hydrogen to helium through nuclear reactions, and as it burns the hydrogen off, it'll start burning off heavier and heavier elements, oxygen and carbon, and it can go on all the way down to iron in the larger stars, and you can get what they call a type 2 supernova from that if it goes that far and it's a big enough star. But most stars will not. Our sun will not do that. It's not big enough. But what they do is they heat up near the end, and they puff off their outer layers, and that's just what's happened here. That star has puffed off all this material from it. The star is in the process of dying. If our Earth were in this system, we would be inside that pretty-looking cloud. Looks very pretty, but if we were there, we'd all be dead now. The heat from the material bleeding off the star would scorch our star and end our life here. And that will happen to our sun someday. And we're looking down the road, probably 4 to 5 billion years, so I wouldn't get too worried about it right now. And this next object is another object, the same type. These are called planetary nebula. Now notice the blue in this one also. And pardon me while I take a quick drink. My mouth has gotten really dry. This is the same type object. The star, the brighter star dead center, is our star that's caused all the problems here. That one right there. Again, it's reached the end of its life cycle and it's puffed off that outer layer. I've understood in the past that blue, a lot of that blue comes from oxygen, and there's some other elements in there that cause that blue. But you can notice the red ring around the outside, that's hydrogen, and there's other kinds of elements there. And this is how our galaxy seeds itself to form new stars and to form in heavier elements like iron. These are called, our sun is what is called a second generation star. It came from material from an explosion from a star many, many billions of years ago that had formed irons and other heavier elements in its structure. So it's not 100% hydrogen and helium. It is mostly hydrogen, and then about, I think, something like 14 or 4% now helium that's converted to, but there's also heavier elements on it. And look around you, you're part of it. Your body's part of it. The table that I've got my stuff set up on here and I'm tapping my finger on, that hard material, that's come from the center of a star, which has burned and produced these heavier elements. Everything comes from the stars. Very, very interesting process. And I think one of the reasons I find astronomy so fascinating. Now we're going to go from desk sites, as these are, planetary number of desk sites, we're going to go to a planetary nursery. This is the Orion Nebula. Boy, the color looks terrible on there. Let's, sometimes these colors don't, that still doesn't do it justice. Let me try changing some things here. There we go, that's a bit better. These are CCD images taken with, this was taken with only a 4-inch telescope mounted on the back of the 10-inch. It's 102 millimeter f7 Orion refractor, and it was mainly used to guide the big 10-inch, but for this field, the object is so big I needed the larger field. The interesting thing about this object is this is something that you could not do with film. CCD cameras you can. This was taken on the night of a full moon. And you all know when you go out on a night of full moon, you can't see very many stars at all. They just get blasted away by the brightness of the night sky. But CCD cameras have a way of looking through that and still being able to produce a fairly nice image. It would be much nicer if it were taken on a night without the moon, but I'm trying to brighten that orange up, the yellow, redder up a little bit, but not doing much. Now I said this is a nursery, and that's exactly what it is. It's a cloud of hydrogen gas, and this is where our stars formed. These little eddies, you can't see them in this image because it's such a wide-angle image, but in the core here, and then there's some other areas out in here, and higher power images, especially if you go to Hubble Space Telescope images, you'll see little dark globules, and those are the birth spots of new stars forming. They're gravitational wells that are sucking in material, and eventually they'll suck in enough that'll turn the radioactive generator on and start producing hydrogen over to helium and setting the star off and giving off heat and light and beginning its life as a star. And our sun went through this, and as I said, it'll go through the death cycle also, where it'll die. But this is where stars are born, in these clouds of gas in our own Milky Way galaxy. And there are bunches of them. They're all different kinds. This is, again, the Orion Nebula. This next one coming up is the Bubble Nebula. This I took with the 10-inch telescope. These are not producing nearly as well as a nice straight image. I mean, I'm copying photo prints here, and they're just not doing a good job of showing the real view. But at least you get an idea of what the telescope is capable of. This is called the Bubble Nebula, and if you look, see this here, you can see this bubble outline right here. It's almost like, you know, remember the bubble stuff you got as a kid and you blew it out and blew these little bubbles? That's exactly what that is. Only it's a bubble of hydrogen gas, and remember we talked about stars blowing their tops and being born? Well, this is a star that went through the planetary nebula stage, blew its top, and that's the outer rim that's left over of the gases from that star blowing off its material. And it's like a bubble of smoke being blown by a pipe smoker, or a kid playing with his bubble stuff and blowing his bubble. Only this is a bubble of hydrogen gas. And again, the rest of that red gaseous material around there, that's material, that's star birth material, stuff that's going to build new stars. Something very interesting in this photo, too, is, remember I said I took these with a black and white camera, but we get nice color images by using the red, green, and blue filters. And you can see a very nice example. You can see a very nice blue star here, And down here, you can see a very nice red star. It does work. The red, green, blue RGB works. It takes the color images, even though it's a black and white camera. Now, this actually, if you find that confusing, just think about the old color films that you used to buy for color film. That worked on the same principle. Instead of having little chips like these cameras do, film had little grains in it that were color film that were sensitive to different kinds of light. They had some that were sensitive to red, some that were sensitive to green, some that were sensitive to blue, and it was processed and put together. You got the color image. It worked on the same principle, only using different materials. It was still mixing red, green, blue, the primary red, green, blue colors to produce the nice colors that we get. Now this next object this was the last CCD image that I had took, and that's been over a year ago, and that's a little blasted, overpowered. This is about an hour and 40 minutes, hour 45 minutes worth of exposure time, there we go, it's a little better. And it's called M17, again from the Messier catalog of Charles Messier. It's a hydrogen gas cloud. This one is loaded with what they call those Bach globules. It doesn't show up real well in this production, but on my real image right in here, in this area here, there's a bunch of them showing up. And those are new stars in the process of being born. This was not taken from the observatory. This was not one of the images that I took from my observatory. This is one of the reasons that when I moved that I do not do the CCD image anymore. I may go back and take a few more because it's such great fun. But on this particular night, I had gone to the White Memorial in Litchfield. It took probably an hour and a half to set up over 100 pounds of telescope equipment, align the polar axis, get it lined, get it tracking right, get all the camera gear, wires, power packs, everything we needed up and running. The computer's up and running. We did it in June, so you're battling mosquitoes. You're playing with power packs for computers on the open field. I mean, it's a real chore. I mean, yes, look at this beautiful image. That's a gorgeous image. And believe me, the real image, if that you could see it other than being shown here on this computer screen, it would be much, much prettier. And it's probably going to drive me to go back and take a few more of those. Although working with the moon out in my back parking lot it's a much easier with these now almost 70-year-old old bones of mine, which have a tough time handling the cold weather, and it's just a little bit easier working on something easier to work on. But that image there is beautiful. There's I don't know if I can adjust the color much, but there's a lot of the reds that aren't really showing up. Here, if I juiced it up some, there up on top, you can see more of it. I blew out the center, but you can see more of it up in here, right there, crossed here and here. You can see a lot more of the outlier, the reds there that show up. And let's see, what do we got? Now we're moving on. We're moving out of our galaxy into another galaxy. I'm looking at 36 minutes in. This is getting longer. I wanted to go, but here we go again, as I usually do, going on way too long. This object is another galaxy. This is the galaxy M33. And it looks like I better take a couple of these off of here. They're starting to take up too much room. This galaxy is located roughly 3 million light years away. You can see the core of the galaxy here, and then the nice spiral of arms out in here. This galaxy is roughly 2/3 the size of our galaxy. It's probably about 75,000 light years across, where ours is around 100,000 light years across. Ours probably has 1 to 200 billion stars. I've heard even higher numbers. M33 probably has 100.5 billion stars. But what I like about this object, and I wish you could see it in a true image on the computer screen, the red showing up in some of these objects right here, right there, that reddish object right there, that's a hydrogen gas cloud in that galaxy, which is a star-forming region. Notice also, notice these arms. See these arms that go out in here, in here, in here, down here. Notice they're all blue. Those are newly formed, very, very young, hot stars. Blue-white stars are the youngest and hottest stars, and they show up very, very nicely in this galaxy. This galaxy is located in Triangulum. It's up in the fall sky. It's a very, very difficult object. I hunted for this object for years, and as a youngster and amateur, I was never able to find it. Finally, when I did locate it with a telescope, it turned out to be nothing more than just the slightest little bit of a haze in the telescope. But as soon as you put some photographic power, or better yet, CCD power like we've done here, as you can see, this thing just explodes into a beautiful, beautiful object. Again, this is roughly 3 million light years away. In other words, the light that struck my computer chip that night to form this image left that galaxy 3 million years ago. That's just really, really something amazing. This next object I'm going to display sideways because it just makes it easier to keep it on the screen. This is the galaxy M51. And this is a gorgeous spiral galaxy. You can see the beautiful spiral structure, the spiral arms in it, and then what looks like a knot attached to the end. Now, there's some controversy that's come up with this galaxy. Once we learned what galaxies were, it was pretty much assumed that this object was one. It was all connected. But lately, because there's been others that have looked at it more closely, and now they think that the big section here with the spiral arms is one galaxy, and this big round object right here is a separate galaxy which is farther in the background. And if you look at it, the thinking is look at the dust arm. See this dust arm that comes down here and goes up through? See the dust arm there, that black arm? Well, it goes up and passes in front of the object over here. So the thinking is that dust arm is in the galaxy, which is foreground to us, and it goes in front of that object that sits in the background. I mean, that's just one point of view. Whether it's true or not, I don't know. But that's a beautiful galaxy, relatively easy to find in a telescope, and beautiful when you image it. And I'm going to end this up with one more image of a galaxy. This one I'm very disappointed with the way it printed. It did not print well at all. It's a much, much prettier galaxy than this. This is called the Fireworks Galaxy. Its number is NGC 6946. This doesn't, I just don't like the way the colors showed up on this, and I don't know if I can do much about it here with the color controls. It doesn't really want to, that's a little bit better if I turn that down a bit, but I'm still not getting quite the color out of it that I want. What I'm after is you've got the bright core, and you've got these arms, and what's really interesting about it is you can see where the red hydrogen gas is built up. You can see hints of it in this arm up here. You can see that's kind of a pinkish color down and through here. There's some also in here and here. And it's like shock waves, which has pushed out and formed these almost like wave-like patterns of hydrogen. And then the blue areas here, which are behind them, right here, are the stars that eventually form out of those patterns of hydrogen and form those bright, new, young, hot stars. Okay, we are 36 minutes in. In fact, it looks like my counter has stopped. No, it hasn't. I'm 45 minutes into I'm looking at the wrong one. We're 45 minutes in, so guys, I'm going to cut it here. I didn't realize we were that far. I kind of lost myself. I hope you kind of enjoyed this trip down, memory lane. I've got so much more stuff here. Maybe some more. We've got the rest of the winter. It's going to be some cold nights. I won't get them out again with the moon for a while. So maybe we can do a little bit more of this the next time. If you enjoy it, I hope you enjoyed it. I hope you got something out of it. Give me a shout out on the comments what you thought about some of the stuff we talked about, what you saw. And we'll probably have time to do a couple more before spring break so we can get back out with the moon again. So again, guys, I'll end it here. I'm going to say, again, it's January 2nd. I'm going to wish everybody a happy New Year. I wish you good health, clear skies, and we'll see you again soon, guys. Take care.